to lecture 27, no, 24. It's January 27th. Soon to be lecture 24 or 27 of Information Theory 2. Today, what we're going to be talking about is basically the most of today's lecture is going to be the proof, the main proof of the rate distortion theorem, and that's the if and only if condition about achievability. And as you're going to see, it's a generalization of what we saw in the context now of channel capacity. And as you'll see, we'll actually also show some sort of geometric analogies to the channel capacity geometry that we studied a little bit earlier this quarter. But in this particular case, it's going to be in the context of, in some sense, rather than bin packing, it's going to be like bin filling. So it's in some sense like a dual discussion. We're still in the midst of chapter 10 of our book, if you're wondering. And also, we still have these outstanding readings, which we haven't actually got to yet. But today, if we have time, in the third non-review section of the lecture, we will begin to sort of discuss the intuition behind these two papers, namely the Blahead-Aramoto papers, which came out at about the same time. I don't know the history that well, but apparently they didn't really talk to each other, and they sort of somewhat independently discovered this idea at almost the same time. So that happens more often than not. I mean, it's, ideas are ripe out of the air. People come up with the same ideas because basically at any given time the community reaches a point where a particular idea, even if it hasn't been any sort of maliciousness or malintent, sometimes ideas become obvious, resting upon whatever happens to be the current set of ideas floating around in the community. So this actually doesn't happen that infrequently. Homework 1 is due tonight. Is that right? 11:45 p.m. online. Has anyone finished it? Has anyone done one problem? Has anyone done 2 problems? Has anyone done 3 problems? Has anyone done 3.5 problems? Has anyone done 3 3/4 problems? I mean, I could keep going with this for a long time. Has anyone done 3.976 problems? So no one's done all of them. So people have done. I would suggest soon after this lecture ends, that you start on the problems, especially if you were one of those who nodded their head when I said, has anyone done 1 problem or 0 problems, which I didn't even ask because I didn't assume, nobody did all these 0 problems. So we do have office hours today. If you want to come by, I will be online later tonight if you want some emergency discussion time. Last minute emergency discussion time. Okay, so as a review, we've been discussing about the general shape of the rate distortion function, the information rate distortion function, and in particular we derived the rate distortion function for Bernoulli sources under a Hamming distortion. And we saw it has exactly this particular form where we have this analytical expression under these different cases. And it has this nice shape which we argued makes a lot of sense. And we've said that many, many times. In particular, what happens, there's this critical point at which the distortion, once the distortion reaches and goes beyond this critical point, we need not communicate at all. And then we also saw a similar phenomenon in the Gaussian source with squared error distortion case. And we have a rate distortion function that takes this form. The only difference really here is what happens again when the distortion gets 0. We sort of get into this sort of infinite capacity phenomenon that we saw in the Gaussian channel case for communication under without power constraints. Okay. And then the third case we studied was when we have multiple Gaussian channels that are independent but must abide by sort of a joint distortion constraint, which is given by here. And then with the joint distortion constraint imposes conditions on or interaction between the channels. In particular, what we found was that the form the rate, this is the rate of these multiple channels, is really just a sum of these rates, and each of the rates have the same form. But what's different about it and where the interaction lies is how the distortion is formed, di. And so we found that di has essentially two classes of values. Either di is equal to lambda for all of those lambdas, which is less than the signal power, the ith signal power. And if lambda is greater than the signal power, then we take di is equal to this thing. And where lambda, we just choose lambda such that this is true. And that gave the sort of famous inverse water filling picture, which we talked about last time. Okay, so what are we going to do today? So first of all, the next few slides are, even though these aren't in the review section, they're just a bit more review slides from previous lectures. So let's just go over these again, because these are going to be necessary. So what we want to do, by the way, if you're wondering, which I hope you are, is you can see the theorem that we're trying to prove up there in the upper left-hand side. It's a title in math. And basically it's trying to prove that the rate distortion function, which is this infimum of achievable rates for a given distortion, is the same as the information rate distortion function, which is the result of this optimization problem. Again, exactly analogous to the theorem that we needed to prove in the case of entropy compression last quarter, in the case of channel capacity, and in the case of the Gaussian channel that we did this quarter. We've been doing this. So at this point, this type of theorem should be familiar to you. But because there's a distortion, there are a couple of other subtle nuances that arise here that don't arise in the previous case. And so therefore, we're going to go over this theorem a bit more carefully than we did the Gaussian channel. So first of all, let's do some review. So again, this is, I think, from 2 lectures ago even. So we have a sort of the rate distortion setup where we have a source. We have sources that are drawn IID from this probability distribution. Okay, and all source symbols come from this alphabet X. And we have an encoder that maps sequences of length n to an integer between 1 and 2 to the nr. And so r is our rate, and that controls how many integers we can map to. So we're limited, in some sense, our bottleneck, in some sense, is this rate. We have a small rate, and we want to have a small rate because we want to do compression, and that means that we can't map to too many integers. So then we have a decoder function, which is, it's sort of an inverse mapper, but it takes one of these integers, and it maps it to a code word. And we only have as many code words as we have integers. So while the code book can come from a continuous alphabet, we only have 2 to the nr possible code words because of the integers. And a distortion function, which is something that measures, it's important because it measures what we consider to be a distortion. This is the distortion. And we have this notion of boundedness, which we're going to assume that and we're going to use that now, finally. This is going to be important for the proof of this theorem. And we saw a bunch of distortions. The Hamming has this property, or the squared error has this property with a bounded input size. So a code, what is a code? Or the 2 to the n or n code. And remember, we're going to be proving things about sequences of this code in n. So we want to show that, for example, there exists a sequence of these codes such that as n gets big, the probability of error gets small, and the rate is bounded by the rate, and the distortion is bounded by the distortion. Actually, it's not the probability of error we care about, it's the rate. It's the rate and the distortion that we care about in the limit. And so we have a 2 to the n code, which consists of one of these encoding functions. Again, remember it encodes n symbols at a time. And a decoding function. And remember, it takes n symbols and goes to a single integer, and then the decoder function takes a single integer and goes to a vector of length n. One thing to note right away, which we're going to use, and I think I put this here to remind everybody, that we can immediately bound this entropy. And the reason why is because there can, even though it's the entropy of this continuous vector valued random variable, x hat n, again, what really matters are the probabilities, and what really matters is it's a discrete probability distribution, and there's at most 2 to the nr of them. So therefore, the entropy is bounded above by log of 2 to the n, which is just nr. So this is a bound on the entropy, which we're going to use. Does everybody see that? So, and then we have the expected distortion, which is this last stuff down here. And that's just basically taking the expected value over the source distribution of the distortion achieved by going through the encoder and the decoder. So it really basically says how bad, weighted by the probability, how bad is a code word for any of the source sequences for which that code word is meant as a surrogate. And that's what the distortion is on average. So here's the first rate distortion function. This is the distortion rate function. Oh, this is actually too bad. So what I wanted to do in this slide is have the rate distortion. Maybe I have this in the next. Do I have that? Yeah. So what I wanted to define was the rate distortion function. So let me just draw it in. So we have the rate distortion function is equal to the infimum over all rates such that is achievable. Right. So this is really the function that we want here. Okay. And so we've got this guy, this infimum function, and we've got this guy. And what we want to do is show that they're identical. Or, to be more precise, we want to show the following. First of all, we want to define what it is to be achievable. And achievable is like this notion that we've seen before in other contexts, but here what we're saying is that a given pair, a pair is an RD pair, is achievable if it is the case that there exists at least one sequence of to the n codes such that as n gets big, the expected distortion doesn't exceed the distortion, the given distortion. Right? So what limits the rate? Well, 2 to the nRn. Right? This is the thing that gives us the rate. So we're given RD, we're given a pair. Okay, so given an RD pair, there exists a sequence of 2 to the nRn codes which limits the rate such that it has this distortion. And that means, okay, that means in this plot, this guy, this RD point, is possible. Or achievable. That's what it means to be achievable. Here's the rate distortion function, which I previously wrote unnecessarily, apparently, because there it is. All right, so here's the key theorem. So RD is the rate distortion function, and RID be the sort of information rate distortion function. Then what we want to prove, and this is going to occupy us probably for the next hour, maybe less, we'll see. Then RD is equal to RID. So it basically means that the result of this optimization, the information rate distortion function, is the limit of achievability. Okay, so we're going to prove a lot of subsidiary lemmas and theorems along the way, which I think are sort of interesting in their own right and delve into the notion of convexity a little bit. And for those of you who are taking the convex optimization class, some of this will seem either familiar to you or enjoyable, because you will see some utility. You'll see the utility of convexity in the context of information theory and rate distortion theory. So basically there are two things to prove. Number one, and we're going to prove them in this way. There's for this theorem, there's the if and only if part, right? So first is that if a pair RD is achievable, then it has to be the case that, here's the first thing. If RD is achievable, then the rate has to be lowered by this information rate distortion function. So given any RD pair supposedly achievable, then the following must follow. And then the second thing, the converse of the theorem, which actually we're going to prove first, which is that if the rate is above the information rate distortion function, then there exists a sequence of codes that can achieve that pair. And again, it's going to be one of these Shannon-style, tantalizing, but it's going to be an existence proof theorem. It's not going to give us the code. It's just going to say that there is one, unfortunately. And again, you know, what happens at this exact point depends very much on the case. We saw, for example, that there's notions of dyadic distributions and other particular special cases for which it may be possible to get exact equality, but other cases where it's not. So it really, you know, since we can say we can get as close as we want to RID, we sort of don't really care. Right? Although there are special cases for which analytically you can actually get equality. But the theorem we're only going to prove is this strict inequality. So let's look a little bit at, so we've already looked at Gaussian sources. So we've mentioned this theorem before, but I think at this point, hopefully everybody is very comfortable with at least the statement of the theorem and the things that we need to do to prove it. So, so the theorem, the converse of the theorem says that if we've got an IID source and we've got a probability distribution and a distortion measure, then any to the NR code with average distortion has this rate right here. Okay, so this is sort of restating it. And here, this is something that one should remember. This bit here. So this is sort of the average distortion. Notice that we're defining. This is almost definitional, like of this thing. So it's the expected value of the distortion for n sequences. So we're taking the average over n, 1 over n of the individual, and then the expected value here inside of this thing here is with respect to p of x. Okay. So we'll use that, so remember. So another way of stating is that for any achievable pair, we have that R is lower bounded, thusly. Now, first of all, I mean, the analogy should be clear. It's saying that if the probability goes to 0, then we can't compress lower than the entropy. Except here we're saying if the distortion is upper bounded, we can't compress lower than this lower bound rate. This is essentially the same thing. Okay. So lemma number 1. Everybody, any questions about that? Everybody see the analogy? Okay, so lemma number 1 is that this information rate distortion function, RID, is on the first of all, it's non-increasing in D, and secondly, it's convex in D. Okay. First of all, I mean, just from to show the non-increasingness, I mean, we've seen these functions and they're sort of decaying off like this. I mean, and one way of seeing that, of course, is that as the distortion gets bigger, we're relaxing the constraint on the optimization, and we're taking a minimum where we have a larger set of things to optimize over, so it can't get any bigger, since the possible solution for a smaller d is always within a feasible set of possible solutions for a larger d. So therefore, it can't be increasing. So it has to be non-increasing. Doesn't mean it's necessarily decreasing. It just means it's non-increasing. Okay. So everybody happy with that? But on the other hand, a little bit stronger result from the perspective of seeing that it has this particular shape is the convexity. And to show the convexity, we have to do the following. So let's show 2 pairs. So first of all, to show that it's convex, it basically means that this is a convex function in D. Right, so if we take a mixture of distortions, right, that R of the mixture of distortions is less than or equal to the mixture of the corresponding rates. That's convexity. So now let's consider 2 pairs, RD, on this RD curve. So there's 2 pairs, R1D1 and R2D2. Sorry, that was unintentional. R2D2, maybe that was intentional. Why? So who is R2D2's forebearer? You didn't realize that there was Star Wars -2, and there was a character called R1D1. And there was another character called R-3, D-3 as well. but that's distracting us. So let's just talk about R1, D1, and R2, D2 on the RD curve. And so we have the corresponding, so it's on the curve, so that basically means that there are corresponding distributions that achieve those pairs. And let's define these distributions as follows. So we have this and this. Now, P of x is the same, right? Because P of x is not what we get to choose. P of x is sort of the source distribution. It's P1 of x hat given x and P2 of x hat given x. Those are the things that sort of determine, really, the difference between the two joint distributions, P1 of xx hat and P2 xx hat. Okay. So let's mix them together, mix the distributions together. So we're mixing the joint distributions together. So this then gets a distortion, which is the mixture of the distortions. And why is that? Well, if we look at this, maybe we should look at this first. So this is just the mixture distribution. P lambda is a mixture. It's a convex mixture. It's also a linear mixture. So it breaks it apart, and we get the two corresponding distributions weighted by lambda and 1 minus lambda, which is this bit here. So let's just define this as d lambda. D lambda is the mixture of the distortions, which comes from mixing the distributions. Okay. Now the other thing which we learned last quarter in like lecture 1 or 2, maybe it was 3. I don't remember, but it was a very early lecture last quarter, and we learned that if we fix P of x, then the mutual information is a convex function of P of x hat given x. Okay. So what this means then is the following: that if we take the mutual information with respect to P lambda, because remember P lambda is just a mixture of the distributions from the P of x hat given x perspective, so that's going to be less than or equal to the mixture of the mutual information quantities, each of which comes from the corresponding distribution P1 or P2. It's convexity of mutual information in the conditional distribution. So then how do we get the convexity of the rate distortion function? Well, we start with this. Okay, so we take this distortion d lambda and we feed it in there, which is here. Right? Now, this is an infimum over all conditional distributions of the information rate distortion function with distortion d lambda, which is the mixture. And that's going to be less than or equal to this, right? Why? Because this is the mutual information using the mixed distribution. There's no optimization. On this side, we're optimizing over all conditional distributions. On this side, we're just plugging in the mixture distribution, which might or might not be the true minimum. So therefore, the information rate function is going to be less than or equal to it. Okay. The next step we do is we use the convexity of mutual information, which we showed, and we get that that's upper bounded by the mixture of mutual informations. But now, remember, we have that P1 was the achieving distribution for the R1, D1 rate distortion pair, and P2 was the achieving distribution for the R2, D2 rate distortion pair. I was about to say a joke there, but I decided not to. And therefore, that those we have a convex combination of the rate distortion functions, and so therefore the rate distortion function is convex because we've got this less than or equal to this. So therefore, I mean, when we see these kinds of shapes, this is what they look like. Yeah.
So it's convex with respect to the conditional distributions, P1, P2? Well, what is it convex with respect to?
So this is the statement that we want. It's the green thing on the bottom. So remember, we're keeping P of x fixed. So look at the definition of these two distributions. We've got P1, which is this, and P2, which is this. And notice that the P1s are the same, right? So or sorry, the px's are the same. So this stuff is the same here. Right, the green part is the same. And it's the orange part that's different. So, and so it's convex in the conditional distribution, fixing the marginal on one side. That's mutual information. That's what we proved, lecture 3 or 2. And so we use the convexity, but we also use the form of the rate distortion function, which is the minimum. The minimization is what gets us the first inequality. So therefore, these are the shapes. These are the shapes we're going to see. Now we're going to use the convexity. We need this convexity. So let's prove the converse. So again, let's just restate the converse. So basically, the converse says, if we have any 2 to the nr encode with distortion at most d, then we must necessarily have that the rate is lower bounded by the information rate distortion function. So then, so when we've got, so is everybody ready? Everybody have any questions about the convexity? Or any other questions? So the first thing to note is that we have the random variable x hat of n is essentially constructed from the encoder and the decoder function. Send x of n through the encoder function fn and g of n, and we've got this thing, right? Which we can think of in some sense as this function of the source sequence. So let's start now with nr. This is one of these proofs, except that in this case we're not starting with 1, we're starting with nr. So nr is going to be an upper bound of, anybody remember? We talked about it a few slides ago. The entropy of the code word. The random variable who has the vector value random variable with takes values in the code word. So this is basically the upper bounding of the entropy. So then we can subtract off the conditional entropy, since entropy is non-negative. This is discrete, right? And now we've got the mutual information. And now we're going to switch things around and express the mutual information in this way. This is the standard. We've done this now 50 times, I think, in this class. And this is all sort of originally from Shannon, the same proof idea and technique. It's amazing. What I think still is amazing that here we are. I don't know how many weeks we've been doing this, and we're still, in some sense, using the same proof paradigm that was established by Shannon in that original paper. That's why I think it's easy to understate how remarkable that paper was. In any event, proceeding with the remarkability of that paper, we can write it as a difference this way because the sources are assumed to be independent. So it's the sum of individual random variable entropies. And then we can express the conditional entropy here as using the chain rule. I guess it's this whole thing. This is the chain rule of conditional entropy, or just the chain rule of entropy, really. And now that allows us to further lower bound this by conditioning reduces entropy, so reducing conditioning increases entropy, which is the negative, so it's the lower bound. And now everything's combinable again. And we've done this exact same thing before. We do a bunch of mutual information twice. And this is lower bounded by the information rate distortion function, right? Because each one of these terms is bound to use whatever distribution this happens to be, but that's lower bounded by the one that achieves the minimum, right? At the current distortion, right? And this is just multiplying, dividing by n. But now this part here is our average distortion. Right? So now, or sorry, I guess it's our average rate, really. Sorry, let me take that back. I skipped a step. So erase that. This part here, now we're going to use the convexity of the rate distortion function. Right? So this is like, it's an average of rates, right? So you can think of it as the probability, the convex combination is uniform with value 1 over n for all of the n terms in the sum, and it's a convex function, and so therefore when we take the rate of the average distortion, that's going to be a lower bound because of the convexity of the rate distortion function. Okay. And so then this is what I was saying before. So this thing is the same as the expected distortion because we're taking uniform distribution over each of the uses of the Gaussian channel. Okay. And d is just equal to the expected distortion, so that's n Ri of d. And so therefore we get as a result, divide by n, we get an Ri is less than equal to this, greater than equal to that. Okay, so that's actually pretty easy. That was the easy part of the proof. Okay. So remember what we proved again was that if it's the case that we have a sequence of codes whose distortion is upper bounded by d, it's sequence of 2 of the NRN codes with upper bound distortion d, then the rate has to be lower bounded. Okay. The next thing we need to prove is the more difficult case, which says that that if we have any pair Rd where R is greater than Ri of d, so in other words, any pair, any value, any set of R and d such that this inequality is true, then there exists a sequence of codes that has distortion d, or at least asymptotically, arbitrarily close to d. So but before we get into this part of the proof, are there any questions about the first part? Yeah.
I'm not sure if this is directly related, but when we have our encoding and decoding function, those are discrete and finite in many code words, right? Mm-hmm. So we've kind of removed all the continuous functions from this problem,
right? Other than the fact that we're measuring the distortion by the resulting code words. Right? So it's not like we've entirely removed the continuous aspect of it, because if we still have to ensure that the code words that we choose are such that the distortion is bounded, because the distortion is a function of the actual values of these code words, not just the number of them. The entropy is a function of the number of them, or as an upper bound, because of the fact that there are at most 2 to the nr of them. So the tricky part, especially in this next part of the proof, the main part of the proof, is going to be exactly that. It's going to be showing that there exists a set of these values that has bounded distortion.
Okay, so choosing where the points are in the continuous space.
That's right. We still have to choose them, because we can't choose any arbitrary points. We have to find them. We have to show that they exist, at least. We don't have to find them, but the proof is just going to show that there are sets of points such that the distortion is bounded. And that's where the proof deviates from. So it's a good question, because that's where the proof, in some sense, that's where the novelty of this proof is, above and beyond the channel capacity proof. Okay, so we're going to again use the notion of typicality. And some of the typicality will be very similar to what we saw in the context of channel capacity, where we have a joint distribution over x and x hats, and we have a distortion function, and we have a value of epsilon, which is greater than 0. And we have a property that we want to ascribe to a pair of sequences, or potentially ascribe to a pair of sequences, called typicality, or epsilon typicality. And that property holds if it's the case that the following 4 conditions are true. The first condition is the notion of x typicality, which is the standard notion of typicality that we know and love from chapter 3, I think. The second is X hat typicality, which is analogous to what we saw before in the channel coding case, except that we called it Y typicality. Now we're calling it X hat typicality. The third is this notion of joint typicality, which we also saw in the context of channel coding. But there's one more that we need, which is distortion typical. And so basically the sequence is distortion typical if it's sort of close in to the expected distortion. So this is the new one. Okay. And any x, any sequence of x such that these things are true, define this set. So we sort of have the original notion of typicality, which is this, which doesn't have the distortion in there, but we're going to define a new one, A, N, D, epsilon, which is the distortion typical set, which is definitely going to be a subset because we still have to satisfy this distortion typical one. So, okay, so there's the bell. Any questions about this?
So if the first three hold, so is it possible that the last one doesn't? Distortion.
Absolutely, because remember the first three have nothing to do with the distortion. The distortion
function is deterministic, right? The
distortion function is deterministic, but the distortion function can choose to measure. You know, the only thing that we're assuming about the distortion really is that it's bounded within the range. So the distortion can, for example, choose to put all of its weight on one spot and give very, very high value. And for a given set of epsilon, it may not actually hold, because you might be putting all of the distortion on one particular set of values or something. So, but on the other hand, and by the way, I think there's a typo here. I think this is supposed to be. I think there should be an extra n here because of the way we've defined this. I think this is right. So I think there's an extra n right there. But obviously, these things need to be balanced. So we define the expected distortion as there being a 1 over n in front of it. So let's just multiply back in an n. Or we could divide the distortion by n as well, just like the average per n distortion. But to answer your question, the first three definitely do not imply the fourth, nor even asymptotically, because the distortion might, do anything. However, what we do want to say is that ultimately, we will have that this set does go to 1, the distortion typical sets. So as n gets big, this distortion typical one happens. So the reason why this happens is because of the weak law of large numbers, just like before.
Could you have a weird, you know how it's very easy to have an expected value that's never achieved, like if you have distribution of integers, then the expected value would be in between like 3.5 or something, but your values only take 3 or 4. Could you have some kind of distortion function where?
No, because it's the weak law of large numbers, and we're dividing by n.
Okay.
And so it's again essentially just saying that if you take an average of a set of things governed by a random variable, eventually it will approaches the true mean.
Okay, that makes sense.
So it's the weak law of large numbers. So it's that kind of thing doesn't happen. Oh, actually, no. Here's the divide by n. So I was actually wrong about this. So we don't need this because we're defining this quantity to already divide by n. So I think we're okay there because we defined this distortion this way. So there is a divide by n, but it's part of the definition. But the point is that we see that this this quantity is going to converge in probability for any epsilon. There's n and a delta and an n naught, such that for any n greater than n naught, this is going to be arbitrarily close. Because it's just the average, it's just the mean value. So now we need to show that we can construct a code and use joint typicality. Actually, maybe we should let's take a short break, because this is a good time to take a break. So let's take a short break and then continue on with this proof. Okay. So we're back. I can see that everybody left the room, came back. I had to wait for quite a long time. Oh, there's the lovely Bell, our friend the Bell, perpetually reminding us that yes, it's once again the bottom of the hour. Just in case we didn't remember that fact. So anyway, so we need to construct a random code. And then we can use, what we're going to do is use, like we've done before, typicality to bound the probability of error and ultimately the distortion. Okay. So first of all, let's fix the conditional distribution. Fix a conditional distribution and calculate p of x hat. So this obviously isn't something we will stick with, but just for right now. Choose an epsilon and a delta, and then show that if we choose a pair that satisfies this inequality, then we can find a code, or that we can show that there exists a code that has no more than d plus delta. And delta can be as small as we want, and that's essentially going to be our proof technique. So we can make the distortion go as close to d as we want if we make the block length long enough. Which, in terms of the rate, is not changing the rate. It just says, well, if you choose a rate that's very small to RID, you might need to use a longer block length, but you can still find a code that does that. Or at least I'm trying to be precise. It's not saying you can find a code, it's showing that there is one. It's also saying good luck finding one. Saying this, if you find, it's good luck. It's like wishing you good luck, saying there is one, but I'm not going to help you in finding one. So that's again one of these theorems. So the method that we're going to use again, this is just sort of the intuition, is the random codebook generation. So script C is going to be our set of random code books, and we're going to have a random. The code book itself is a random variable, which, like in the channel coding case, is itself random. I'm going to take expected values over this code book, as well as expected values over other things, and show certain properties are true of the expected value over the random codebook variable, which must mean that there are at least some good code books, and that's how we're going to do it. Now, obviously, there's going to be a lot of these code books, just like before in the channel capacity case, but from the perspective of an existence proof, that's perfectly sufficient. So what does it mean to generate a random code book? Well, we need 2 to the nr code words. And each code word is basically a vector of length n. So notationally, in case this isn't clear, these are our, there we go. This is our code book. Right? So we have the index, the integer w, which ranges from 1 to the nr, and each integer indexes a length n code word. Okay. All right, so that's what I just said. So we need this many length n sequences, and we're going to draw them IID from this distribution that we acquired from here. And everybody knows the code book. We're going to use W to index it. I think this is pretty straightforward. Okay, so how do we encode things? Well, so we've got a sequence of x. So remember, we choose this, and this is chosen again according to p of x n times. So we've got a particular p of x, and we need to choose a code word for it. And we're going to use typical set encoding. Typical set encoding says, okay, well, we find an index w such that this sequence is jointly distortion typical. Okay. So, if somehow we manage to sort of construct this set, and we go through all w, and we find the one that makes it jointly typical, if no such W exists, because it might not exist. Because remember, we're choosing these things randomly, and for any particular one, it might or might not exist. Then we just set W is equal to 1, and we just are going to accept that that's obviously going to be an error. Or if there are more than one, if there's more than one that's jointly typical, then we can either choose arbitrarily or choose the first one. It doesn't really matter, because what we're going to see is that both of those things happening have probability that's going to go to 0. So we need NR bits to describe the code words, right? It's clear. And so how do we decode? What do you think? How should we decode? So decoding is basically we've got a W.
Find the pair which is jointly typical.
We find the pairs that are jointly typical. So we've got an integer. You don't need to find integer typicality. Right? Because, I mean, we have this mapping, so for every single integer, we have a vector. Right? There's nothing we do. The code book is sitting there. Right? Once the code book is there, once we've chosen this random code book sitting there, we have this massive table, if you will. It's to the NR. Maybe we have this many code words, and each code word is of length n. And so each code word is going to be sort of like a length n string. It looks like this, right? So this is a code word. So for finding, for encoding, we have some source sequence x of n, and we need to find the W that indexes a jointly typical code word. But once we map and then with that integer, then that's what we encode. Then when we decode, we just sort of say, well, that's the code word. Okay. So we can then compute the average distortion over both code words and I think this is probably not the right way of saying this. This is the average distortion over code books and source strings. So let me change this. This should say source strings. And it's average over code books because we're taking the average with respect to P of C, and it's the average over source strings because we're taking the average with respect to P of xn. Okay. So this is important. We're taking the expectation over both the code books, right? So this code book is a random code book, and based on the probability of the source strings, which is the second thing. Is this? I'm not going to ask. Am I going too slow? Is this just right, too slow, or too fast? Just right. Okay. This is the Little Red Riding Hood question, right? Is that right? Is that the right fairy tale? Oh, you're right. It's Goldilocks. Thank you. I haven't brushed up on my Grimm's fairy tales, which I think it's probably not even a Grimm's fairy tale, is it? You tell me. I don't know either. That's okay. This is information theory. This is not English literature, as you can tell. So, okay, so we've got an epsilon, and we're going to divide the sequences essentially into two categories, those for which we have errors and those for which we don't have errors. First of all, category A is going to be those source strings, x of n, such that there exists a code word that indeed is jointly distortion typical, and so for those which are jointly distortion typical, we're going to have, and we're going to meet this distortion bound with epsilon slackness. Okay. Now the other ones, the probability of these sequences, thanks to the joint typicality, is going to go to 1. The other ones, on the other hand, is like, for example, that there exists no W that's jointly typical, And let's say that P of E is the probability of these sequences. This is the probability of the error. Right? And now we're finally going to use Dmax. And so Dmax is the maximum distortion. So then the total distortion for this set is going to be PE times Dmax. Now why is that? Why? So basically, PE is going to be the total distortion is PE times Dmax. So PE is sort of the probability of all of the sequences. And what we could do is we could sort of sum over them. We could sort of sum over all of these sequences, like X in this set, get the probability, right? And then the distortion, which is this distortion here, is going to be less than or equal to Dmax. And so when we get that out, we're going to have Dmax times PE, which is this bit right here. Okay. So I'm not going through that step explicitly, but it's the same kind of thing that we've done. Yeah.
So PE is the probability that it's not a jointly typical sequence.
I'm sorry, say again?
PE is the probability that it's not a jointly distortion typical.
It's the probability that there does not exist a W. So that we can't find. It's the probability of an error. So an error is basically saying we searched through this big giant code book, and I'm sorry, we can't find that's jointly typical. So it's something that it says that there is no jointly typical sequence in our code book. It's not saying it's not jointly typical. It's saying that there doesn't exist a jointly typical code word for our given source string.
And Dmax is different than maximum allowed distortion, right? It's the bound on the distortion.
Dmax is just the bound on the distortion. It's just it's a property of the distortion function. And remember, we've been assuming that there is some value Dmax for which the distortion can never exceed, which can happen based either on the property of the distortion function, like for example in the Hamming distance case, or it can happen jointly based on the properties of the distortion function and some, say, ball limit on the input values. Like if we restrict and say there's some sphere within which the source words have to lie within, then we can produce a Dmax. So that's also a way of getting it. If it's the case, for example, we use squared error distortion. Okay. So then what is the total distortion? D hat, which is this expected value. And that's going to be then, it's upper bound by this partitioning, so either we're going to get distortion D plus epsilon, or if it's out of that set, if it's case B, we're going to get PE times Dmax. That's an upper bound on the distortion. And what we want to do is show that this thing gets small, or this thing gets small enough. And what we can do first of all is, this is going to be something that is D plus delta, and we want to be able to show that we can make delta as small as we want. Oops. And that's possible to do if it's the case that the probability of error goes to 0, as n goes to infinity. So basically, epsilon can be chosen as small as we want because we can choose this. Because of the weak law of large numbers, for any epsilon, there's going to be some point at which everything lies within the joint distortion epsilon typical sequences, and so epsilon can be made as small as we want if we're allowed to make the block length fine. So epsilon is fine. Its Dmax is a constant. So everything sort of rests, being able to do this, everything rests on the probability of error going to 0. So we're back now down to this probability of error problem. And this is where it's a little tricky. It's not that tricky. It's a little bit tricky. So we're going to do the general idea first, and then we're going to go through it in a little bit more detail. So here's the general idea of bounding the probability of error. So the probability of error is going to be, first of all, upper bounded by a particular pair not being jointly typical. Like, for example, that's the probability of these two sequences not being jointly typical. And it's also, we're going to see it's going to be upper bounded plus this other quantity. And this other quantity is going to be the thing that helps us to connect the rate to the information rate distortion function. So remember, we have this this RD pair, what we're doing is we're assuming we're given RD such that R is greater than the information rate distortion function Ri of D, right? And that assumption is going to allow us to say that this exponent is going to be something that's positive and therefore decreasing with n, and so therefore this exponent is going to go to 0. So this first part we get right away just because of joint typicality, and then we can make that as small as we want. That's smaller than epsilon. It's the probability of a pair not being typical. The second thing we're going to get going to 0 if this is the case, if R is greater than the mutual information plus 3 epsilon. And again, since epsilon can be made as small as we want, it's really just that the rate has to be greater than the mutual information. But then what we're going to do also is we're going to, in order to make this true, we're going to choose the conditional distribution, P of x hat given x, to be the one that achieves this rate distortion, information rate distortion function. So what ends up happening, let's just zoom in on this right-hand side thing. This guy here, instead of this, we're going to do, this is going to turn into R of I of D, right? Which is a lower bound. As long as the rate, since we've chosen R greater than this, we've chosen this R to be greater than this value, this whole thing is going to be, this bit here is going to be greater than 0. And since we can make epsilon as small as we want, we can make 3 epsilon as small as we want, and eventually that 3 epsilon is going to be smaller than the whatever the R minus thing is, and that's going to make that whole thing happy. Happy in the sense of going to 0. Everybody with me? Okay. And this is going to give us this thing, which is clearly going to go to 0. So this then says, this is, we're not done yet though, because this is sort of overall randomly chosen code books with rate R and codes, and so this is sort of the expected distortion. What we need to show is sort of an existence. And so what that's going to mean is that since it's an expected value over all of these random code books, there has to exist at least one of them that has that property, namely that rate and that distortion. Because the expected value is true, and this is something you can always show. If you can show something true of the expected value, this is sort of, again, similar to what ended up becoming known as the probabilistic method. If the expected value is true, there has to be one for which it's true. And then deltas can be made as small as we want, again. And so therefore the rate is going to be achievable if R is greater than D. So let's go through it in a little bit more detail. So we need a couple of theorems. First one is sort of a funny theorem. It says, for all distortion epsilon typical pairs, we have that the probability of P x hat n is lower bounded by the conditional of P x hat n given x n times 2 to, it's all written there. I'm not going to say it. But it basically is 2 to the mutual information, negative n mutual information stuff, plus some epsilon fix up. So how do we prove it? Well, we start off with basically a pair that's presumed to be distortion epsilon typical. And just using conditional probability, we get this, which then we can multiply by 1 to get the following. Sorry, there's a typo here. Does anybody see where the typo is?
Should it be conditional and it's numerator?
No, it's not conditional in the numerator. I'll zoom in. Anybody see it now?
I see that at symbol.
Yeah, I'm missing an at symbol. Is that better? Okay, so there we're going to get that. Which again, still missing. But in the second part, it's fine. So basically, now we're using these bounds, the joint typicality, namely that this probability is upper bounded by this, and this probability is lower bounded by this, and this probability is lower bounded by this. Okay, and then basically we're done. Because we got this in the mutual information form, and we just rearrange things, and then you get this resulting inequality. So this is going to come up in a funny time, so I'll try to we'll probably all forget this, but remember, this is the theorem that says P of x hat is lower bounded by something which involves the conditional. Theorem 24.3.5. The next one is kind of a nice theorem, and this is sort of an interesting property in and of itself. So this is an inequality that says that if you have x and y both between 0 and 1, and n greater than 0, then we've got this value here. So this is to prove this, we need to use a little bit of convexity. So first of all, let's just define f of y to be equal to e to the negative y minus 1 plus y. And if that's the case, with that definition, then we immediately see that f of 0 is equal to 0. And secondly, if we take the derivative of f with respect to y, that's going to be equal to e to the negative y plus 1, which is always going to be greater than 0 for y greater than 0. So what does that mean? When you're 0 at 0, and the derivative is greater than 0 for all y greater than 0, what does that mean? That means that you're non-zero. You can't go below 0, because you can only be increasing. So f of y is positive. So this f of y, where again f of y is defined this way. F of y is positive for all y greater than 0. And so what this means, since f of y is positive, this basically means that, since this is f of y, it means that this inequality is true. And here we're just restricting y to be between 0 and 1. So this is really, in some sense, a variational, this is sort of a simple proof of the variational lower bound of e to the negative y. So 1 minus y is a variational lower bound of e to the negative y. And you can sort of see this in this picture. The proof that the thing that we're concentrating on is this range between 0 and 1. But it's also true everywhere else as well. Okay, so 1 minus y is less than or equal to e to the negative y, where it's tight at 0. Right? So we're going to use this in the next page. This is the thing we're going to use. Now, if we take it to the nth power, so we have 1 minus y is less than e to the negative y. You take it to the nth power, then that's already a theorem that we want if we set x is equal to 1. Remember, the theorem that we want is this thing. If we set x is equal to 1, we've got 1 minus y to the n is less than or equal to is equal to e to the negative yn. But what we need to get it for is for the case for other values of x. We can also check that it's true for x is equal to 0. Right? When x is equal to 0, we've got, just going back to the theorem, 1, which is less than or equal to 1 minus e to the negative yn. Right? Which is clearly true, because e is always non-negative. So let's now define this function, gy of x. It's sort of a function of y, but function of x, but parameterized by y. Take the second derivative and show that it's convex. Okay, it's easy to do. And so then if we take x in the range that we care about, because remember, we only care about y between 0 and 1 and x between 0 and 1. We take x in the range that we care about, and we plug it into this value. This is g of y of x. Right? And it can be written as this sort of funny convex combination. X is equal to 0 times 1 minus x plus 1 times x. Which, since x is between 0 and 1, that's the convex combination. The convexity is 1 minus x times gy of 0 plus x times gy of 1. right? And then we plug those values in, we get this thing, right? It's the result from convexity. And when we then use the theorem that we just proved, right? We've got 1 minus y, where is it? It's right here. 1 minus y to the n is less than or equal to, so 1 minus y to the n is less than or equal to this stuff. Okay. But how do we get this last bit? Because x is between 0 and 1. And with x between 0 and 1, we just get it bigger. So basically what we've got, now we've got the theorem. Okay. Everybody happy? I don't know. Go through it on your own time if it's not clear. But the main point is we're going to use this result. Okay? We use this to prove that there exists a code. So how do we do this?
You know, in math, there's a word for subsidiary theorems. They call those lemmas. Or...
Yeah, what did we call it a lemma? Did we not call it a lemma? I don't know what we called it. Yeah, so subsidiary theorem, yeah, lemma. You're right, I could just call this a lemma. This is basically done in order to make a lemma seem more important than it really is. So I thought I would get that one past you, but you are all too clever to see. You're too clever for me. So indeed, this could probably better have been called a lemma. So the next thing, now getting back to a non-subsidiary theorem, which is what sometimes you call theorems. We have the achievability of non-subsidiary theorem 24.3.1, which basically is something where we've left off where we say, okay, well, we need to show this existence. Okay, and so we're going to compute the probability of error for some randomly chosen source sequence. Okay, and we're going to do this as follows. So we're going to first of all define for a given fixed code book C. Well, I'm going to say this is going to be the set of source sequences that have distortion epsilon typical cohorts. Okay. So it's all source sequences for a given codebook that are in some sense good. You can call these guys the good ones because those are the ones for which we're going to be able to find distortion typical cohort. Okay. So then we can construct the probability of error as follows. So here's the probability of error. So just definitionally, the probability of error summing over all codebooks is summing over C, right? So C, and then we have the probability of C, and this is this random codebook generation. And this is the chance that there's an error. It's basically looking at all source sequences that are not within these good source sequences for the given codebook. And then looking at that probability, which is this part there. Okay. Now we're going to do the old, it's a very deep technical mathematical technique called the old switcheroo. And the old switcheroo says that, well, we can write this as summing over all source sequences, and for each source sequence we're basically going to compute the probability of all of those code books for which that source sequence it was never good. It's the same thing, right? It's just sort of row versus column summing of a sparse set versus column versus row summing of a sparse set. Same thing. And if that isn't clear, draw a little matrix with holes in it. Now, when we write it in this form, okay, we're summing over all source sequences. And what is this thing here in words? So this thing here in words is basically it's the total probability over all of these code words, and there's 2 to the NR of them, not being distortion typical with the current source sequence, x of n. So it's, in other words, it's sort of like, for the given x of n, it's the probability of choosing a bad code book, right? And we don't want such code books, right? We only want good code books. But this is the probability of choosing the bad ones. And so this, in some sense, doesn't really depend on the particular source sequence anymore, because it's all symmetric in some sense, right? Because it's sort of saying, well, what's the probability of a code book being bad for some source sequence? Well, it's just Q. And then how many code words are those? 2 to the NR of them. So it's basically raising Q to the 2 to the NR. So it sort of simplifies the expression greatly, because we've now eliminated from anywhere in that inner expression anything mentioning the source sequence. And this is, again, similar to what we did in the channel coding case. It's basically saying, well, because of the averaging over all code books, and everything in some sense sort of having its place, we can essentially sort of treat everything identically once we're taking the average. And then once we treat everything identical, then we can remove it from the averaging process, which is exactly what we can do now, because we have this constant. So Q, again, is the probability that a single random code word is not jointly typical with the current X. And again, because we're summing over all C's, and because C is in some sense, it's sort of this, it has this symmetry property, it's the same. Right? So K is going to be sort of our indicator of joint typicality. This is just for simplicity. So K is basically an indicator of saying that xn and x hat n are jointly typical. And we're going to take expected values with respect to that indicator in order to turn them into probability. So what is Q? So Q is really equal to, it's the probability of, for a given x, source sequence x, and the random variable x hat not being jointly typical, right? Which is really the same as the probability of k, of the k indicator being equal to 0, which is 1 minus the probability of this k guy being equal to 1. So this might be a little bit difficult to parse, so let me fix this and add some parentheses. So maybe I should have done this in the slide, but this is the probability there. I think that's probably sufficient to make it readable. So it's 1 minus the probability of k equaling 1. And the probability of k is equaling 1 is basically just, now we can sum over everything, because we sum over all of x, and here, all of x hat. And it's just the probability of k being 1. All the x hats that for the given source sequence x is not jointly typical. Okay, so now how do we get that next step? Anyone recall? It might have been another subsidiary theorem that was proven. Well, it's the same thing that I said we're probably going to all forget, including me. But remember, it was this bound on P of x? It was the bound on P of x that said P of x is less than or equal to all of this junk. That's not junk. It's actually very, very nicely expressed mathematical formula. But basically it's saying P of x of n is less than or equal to that other green stuff at the bottom that I just outlined. And so that allows us to give us an upper bound. So do you remember that theorem? It was the first of these subsidiary theorems that were proven. That's right. So it was proven from theorem 24.3.5. So you can go back to it. But you're right. I should call it a lemma. I don't know. No matter. no matter how much you work on these slides, one can never say it's bug-free. So, okay, so with this value of Q, and this upper bound of Q, we can now sort of bound the probability of error finally. So we have this expression, which we saw before. Okay, so this now, we're going to plug in the value of Q, right? So Q is this upper bound that we just did, right? So here, we're going to plug in this whole Q is less than or equal to all of this stuff. We're going to plug that value of Q into this expression here, into this little guy Q. This little guy Q right there. And that's going to expand it into this massive thing. So here's the massive thing. All right, so this whole thing is the upper bound on Q. Right. But now we can sort of start breaking this apart. So remember that other theorem that we proved by lemma, I should say. Let's rename these quantities that are bracketed. So let's call this value 1. Let's call it 1 for some reason. The next quantity in brackets, let's call it y. The third quantity, let's call that guy x. And up in the exponent, let's call that n. I know it's a little bit of an overload to call to the nr n, because n appears twice. But maybe it's not so bad if you actually look in on it closely. You see there's a great distinction between 2 to the nr and n. One of which is that the font is different, right? The other of which is now I've highlighted one in green and the other in yellow, which makes a really big difference. But I hope that there's no confusion between these different n's, right? One is for those of you who are into fonts, a serif font, and the other is I don't know, I'm making this stuff up. I don't know what kind of font it is. But in any event, it's a different n. The reason why we're doing this is because what we want to do is express it in this way, where we have this expression, and we have a bound for this expression, right? Because everything lies within what we need. X and y are going to be between 0 and 1, right? This is an expected value of a value between 0 and 1. So that guy lies between 0 and 1. This is 2 to the negative something. And that's going to be between 0 and 1, because the mutual information is positive. So everything is happy. And so we can now use that bound that we saw before, that upper bound. But remember, again, this n, let's zoom in on this again in case there's confusion. This n is not the same n. This is just the n that we used in that earlier lemma. Okay? So let's use that bound now, that variational style bound. We get this form. So now all we've done is we've just used that between here and here. Which then, once we plug back in the definition of x and y and strange font n, we get 1 minus this expected value. Now this looks really nice, because this is now an expected value of this indicator of typicality with respect to a joint distribution. That's probably something we can bound. And then the second bit is probably also something we can bound, again, because of this fact that we're assuming that r is greater than the rate distortion function, and so we can sort of replace the mutual information with its lower bound, the rate distortion function, once we've done that optimization. In fact, this first part is just the probability of atypicality, because this is the probability of typicality because of the way we've defined. This part here is the probability of typicality, and when we do 1 minus that, it's the probability of atypicality. And that's going to be less than epsilon. We can make that as small as we want, basically, is what that means. The second part also goes to 0 whenever r is greater than the mutual information function. And r can be greater than the mutual information function whenever we choose the conditional distribution p of x hat given x to be the one that achieves the information distortion function. So we choose that conditional distribution, And our assumption has been that R is greater than Ri of D. So therefore, this whole thing is going to be true as long as we can make epsilon as small as we want, and we can make epsilon as small as we want. So therefore, that second quantity here is also going to go to 0. So that basically is the proof, right? So we had the expected value going to 0, and we've shown that all of these quantities, all these error quantities, go to 0. We've got the distortion, and we know that there amongst this vast assortment of code books, there exists at least one of them that achieves the distortion. So it's a little bit involved, a little bit more involved than the other theorem, but on the other hand, I think it's remarkably identical. Okay, so are there any questions? Now you might wonder, like, why? Is anyone wondering why we're going through the machinery of this proof, of the proof technique? And I think the reason why is because I'm hoping at least that there's something in what I'm saying that helps with the intuition of understanding this proof. On the other hand, I think it's important to sort of understand these proofs because as you go on in your career, whether it's in information theory or communications theory or somewhere else, understanding the mathematics of these techniques, these proof techniques, and how convexity can be used and applied, because this is really an application of convexity. It can be useful for you in whatever research endeavors you end up pursuing. So that's another reason why I like to do these in class. What I want to do now in the last roughly 10 minutes of class is sort of give a little bit of intuition as to the geometry of rate distortion and see how it's analogous to the information, to the geometry of the channel capacity. So remember, in the channel capacity, let's review this, the channel capacity geometry. In the Gaussian channel case, this is now not rate distortion, this is channel capacity. Okay, and we had a Gaussian channel where y is equal to x plus z, where x is our source, y is what we receive, and z is a Gaussian channel. So z is a Gaussian with noise profile sigma squared, and then x is a source with power p. And we're assuming independence. And we sort of intuitively proved the channel capacity theorem by looking at the X set typical volume, which this is a volume. So remember, we sort of saw that the entropy quantity was really the exponent of a volume. So 2 to the n entropy is that volume. It's that n-dimensional area. For just x, and then we also have the y given x conditional typical set volume, which again is using the conditional entropy, but in this case it's a volume where the conditional entropy is the exponent of the volume. And since it's conditional entropy, it's the same as the noise volume. And then lastly, we have the y, the unconditional y volume. And everything is Gaussian. So this is upper bounded by a Gaussian. This, I think, should just be equal to a Gaussian. The entropy of z is equal to a Gaussian. This is the Gaussian entropy. This is the upper bound on the Gaussian. This is the Gaussian entropy on the right-hand side, which is an upper bound of the entropy of the received symbols. And so what this allows us to do is to do this sort of bin packing, where we divide the noise profile volumes. Remember, we had these sort of little balls fitting into the big ball. And we want to pack as many of these little balls into the big ball as possible, and without there being an overlap. And if we can do this in high dimensions, we essentially just divide the big volume by the small volume. So here's the big volume, which is, this is the big volume, which is 2 to the n hy, and the small volumes, which are 2 to the n h of z. And we just divide them together, and we essentially get this or this quantity, which gives us the signal-to-noise ratio rate. Because once we convert it into bits and convert it into per channel use, which divides it by n, it's the number of channels, number of times we use the channel, we get this the famous rate thing. just from a geometric discussion. Okay. And then when there's no overlap, we get that the rate is equal to the capacity. Because as soon as we try to fit more small balls into the big ball, we're going to get overlap, and we're going to start getting error. So this was the sphere packing idea, or the bin packing. I mean, I'm not sure if it's necessary to go through this again, but remember we sort of equated it to an n-dimensional sphere with radius r. We computed these radiuses, and we sort of got this expression in terms of m, which was the number of messages. Right? And the rate was, remember, log m over n. Number of bits divided by the number of channel uses to specify m messages. So what we can do, the goal here, the goal again is to pack as many small spheres into the big sphere as possible without there being overlap. Because we're trying to push as many bits through this channel as possible without there being overlap. So what's the geometry now of rate distortion? Which in some sense, as we'll see, is a little bit of a dual. So we've got a source which has signal power, sigma squared. And we've got a 2 to the NR code, it's got a distortion. And we've got a code book with 2 to the NR code words. And hopefully most, I mean, if it's good, if it's low distortion, then basically each source sequence is in some sense close to at least some code word. You know, the code word that is meant to be a surrogate and as a representative of any source sequence should be close relative to the distortion measure. So the sources in some sense live in this sphere. Right? You think of it as living in this massive sphere with radius as given. And the goal is in some sense to use the fewest number of code words so that every source sequence is close, and by close, in order to achieve the distortion, we need to make sure that there's no source sequence that is in some sense farther away than the square root of nd from its closest code word. So what is the technique? What is the sort of geometric analogy? So in the case of the sphere packing for channel coding, we sort of wanted to pack in as many balls. Like we've got this big bag, and we try to put in as many balls as possible, and we want to sort of uniformly paint the space with small spheres inside of this large sphere. The geometry in rate distortion is that, well, we've got these sort of fixed sphere things, but we want to make sure that there's no point that's very far away. So we want to sort of spread these things out within this ball. We want to spread them all over the place. And we want to do this minimally. We want to sort of put the minimum number of, I mean, it's okay if we put in more balls from the distortion perspective. We could put in lots of balls, we could have overlapping balls, and from a distortion perspective, we can put in as many balls as we want. And we'll get that distortion. As long as any point you choose is close to the center of one of these balls. But what we want to do in this case is put in as few balls as possible, while still, in some sense, covering the large sphere. So that's the sort of dual nature of this problem. So the minimum number of such words that has this property, that is such that any source sequence is close to the center of some ball, is basically going to be taking the volume of the big sphere divided by the volume of these small spheres, right? And that's going to be, it's going to have this form. And that's going to be 2 to the NR.
That seems like an easier problem. Is that fair?
Easier from what perspective?
Like I know sphere packing was like a major unsolved problem in math for a long time, in 3 dimensions or something. And then this is like a set covering seems like.
Is set cover? Set cover is an NP complete problem. So they're both hard. I mean, combinatorially. But what we're going to see, and especially what we're going to talk about on Wednesday, obviously we're not going to talk about it today, is that so next what we're going to talk about is how to compute the rate distortion function more generally. So here's, this is the rest of this discussion. It's basically the same thing I've already said. So we just want to sort of spread these small spheres out as much as possible, put as few of them as we want. Put as few of them as possible into the large sphere. What we're going to see, however, is that when we want to compute the methods, first we're going to talk about the sort of Blehett-Aramoto procedure. So this is really a good time for you guys to read this. And we're going to get kicked out of the room in 1 second. So, but what we're going to see is that the general way of computing the rate distortion function in terms of hardness is exactly the same general way of computing the channel capacity function, which is the method of alternating minimization, which is a type of convex optimization procedure. So we'll begin to talk about that probably on Wednesday, the alternating minimization. But you can read, I would definitely at this point read the Blehett and Aramoto papers, at least to look through them, because that's what we're going to be doing next time. Okay, any other last minute questions? Okay, I will see you guys Wednesday.